This is section 11.5, part 5, and we're now going to take a look at the geometry of lines in 3-space. First of all, just a quick reminder, in 2-space there are essentially 3 relationships that 2 lines can have to how they're situated with respect to one another. Right? One possibility is that the 2 lines simply intersect. Another possibility is that they are parallel. And the third possibility is that they're collinear, or in other words, they're really the same line. Now, in 3 dimensions, you can have these same 3 relationships, but there's also a 4th possibility. In 3 dimensions, it's also possible that 2 lines are skew, meaning they're not parallel, but they exist in parallel planes, and therefore they never intersect. Just help you see what I mean by that. Imagine these 2 lines here. Clearly right now they're intersecting, right? They're crossing. If I were to take these 2 lines, they're not parallel, but if I were to just pull them apart this way, they still are not parallel, and yet they'll never intersect because they exist in parallel planes. We call those kinds of lines skew. Non-parallel, but existing in parallel planes. If I were to try to sort of show you what I mean by this by sketching, if you simply sketch a couple of parallel planes here, maybe line 1 is down here in this plane, and maybe line 2 is up here in that plane. They're not parallel, they don't have the same direction vector, and yet because they're in parallel planes, they will not intersect. Our goal in this last part of this section is going to be to take the equations of 2 lines and determine which of these 4 situations we're in. Are those 2 lines intersecting, parallel, collinear, or skew? So how can we do that? Well, here's supposedly our 2 lines, R1 and R2. Notice because they're different lines, I've used a different parameter for each one. I used the parameter T in the first line, so I just used a new parameter S in the second one. How can I decide which of these 4 cases I'm in? Well, first of all, the direction vectors, V1 and V2, tell part of the story. Notice that with parallel and collinear lines, the direction vectors are either going to be the same or they could be multiples of one another, right? They have to be parallel to one another. So I could have identical direction vectors, or one may just be longer than the other, but they point in the same direction. Whereas with intersecting and skew lines, they really do point in different directions, so their direction vectors are not multiples of one another. So let's start with that. If the first direction vector is a multiple of the second direction vector, so the direction vectors are parallel, then the lines are either parallel or collinear. I'm going to come back to that in a minute. If V1 is not a multiple of V2, so the direction vectors don't point in the same or opposite directions of one another, then that leaves us with intersect or skew. All right, so now we're down to these 2 to tell apart and those 2 to tell apart. It all comes down to the intersection. If I know that my lines don't have parallel direction vectors, what I'm going to do is try and find an intersection point. If I find one, then the lines intersect. If there is no intersection point, then they're skew. So intersect, this is going to sound silly, but if an intersection point exists, And they'll be skew if no intersection point exists. I can use that same kind of logic with the parallel and collinear. Of course, the collinear lines will have infinitely many intersection points, but as long as I can find at least one, the lines will be collinear. They'll be parallel if I find no intersection points. So parallel if no intersection points exist. And collinear if there is an intersection point. Again, allowing for the fact that even if one even exists, there'll be infinitely many, but all I have to find is one. And I know that they would be collinear in this case. So how do I go about determining that? Well, let's take a look at a few examples. In these three examples, I want to know whether each set of lines is parallel, collinear, intersecting, or skew. If they intersect, we'll actually find the intersection point. So let's see here. In the first pair of lines, it looks like I wasn't even nice enough to give it to us entirely in standard form, so let's do that first. R1 is 3t minus 2, 2t plus 0, and 3t plus 0. And R2 is s minus 6, 2s minus 8, and 3s minus 12. All right. For starters, let's think about the direction vectors. The direction vector for the first line was 3, 2, 3. And the direction vector for the second line was 1, 2, 3. Clearly, there's no multiplier that I could put on one of these vectors to turn it into the other one. The second and third components are identical, but the first one's not. So no way is V1 some multiple of V2. So right away, they can't be parallel or collinear. It means that they're either intersecting or skew. And my next job is to figure out which of those two cases it is. So now I'm going to try to find an intersection point. In order to do that, I'm going to say that if these lines intersect, then the x values have to be equal to one another, so do the y's, and so do the z's, right? They only intersect if all three components match. So I'm going to set them equal. For the x's, I would have 3t minus 2 equals s minus 6. For the y's, 2t equals 2s minus 8. And for the z's, 3t equals 3s minus 12. I'm going to go ahead and just change these into standard form. I'm going to put my s's and t's on the left and the constants on the right. So I would have 3t minus s equals negative 4. 2t minus 2s equals negative 8. And 3t minus 3s equals negative 12. Now when you get to this point, the system of three equations and two unknowns, you need to solve that system. And it doesn't matter to me how you do it. If you're quick and it's easy for you, feel free to use a substitution or elimination method, solve by hand. Otherwise, you're more than welcome to use a calculator method to do that. That's what I'm actually going to do here just because it's fast. In my apps menu, I have my little polynomial solver, or you could use a matrix method if you don't have that. I'm going to solve my polynomial or simultaneous. Boy, I can't talk. I'm going to solve my simultaneous equations. And in this case, I have 3 equations and 2 unknowns, so this is set up just fine. I'll keep my answers on fractional and everything looks good, so I'm going to go to next. And then I just need to put everything in. My first row would be 3, -1, -4. My next row, 2, -2, -8, and then 3, 3, -12. Looks like I might have used this last time for the same problem. All right, hit solve, and I get x, which in my case is actually the t's. So t is 0, and s is 4. Again, you can use a matrix method on your calculator. You can do it by hand using like an elimination method or a substitution method. However you would like to do your systems is perfectly fine with me. All right, so in this case, I am going to be able to find an intersection point. So I now know that these lines are intersecting, not skew. And in order to find the intersection point, I can either plug t equals 0 in here, or I can put s equals 4 in there. It should turn out the same way. It would be R1 of 0. If t is 0, that would give me -2, 0, 0. And although we don't really have to do both, just to prove it to ourselves this first time, let's plug 4 into the second one. R2 of 4, 4 minus 6 would be -2. 8 minus 8 is 0, and 12 minus 12 is 0. So I now know not only that the lines are intersecting, but that they intersect at the point -2, 0, 0. All right, let's try B. Let's see, these were given in a little bit nicer form, so I won't rewrite them this time. They're right up here. And I want to start again by examining the direction vectors so I can at least get myself down to 2 options. This time, notice we're going to have to pick out the direction vectors from the equations. So for V1, that's really a 1t, a -2t, and a 3t. So my direction vector is 1, -2, 3. My second direction vector is -7, 14, -21. All right, this time it looks like I do have a multiple. If I take V1 and multiply by -7, I'm going to get V2. So that tells me that these are either parallel or collinear. At this point, I'm going to go ahead and just like I did up here, I'm going to try to find an intersection point. If I find one, they'll be collinear. If I can't find one, they'll be parallel. So let's go ahead and try and find an intersection point to decide whether parallel or collinear. And to do that again, I'm going to set the x's equal to one another. So I'd have t plus 4 equals -7s plus 1. And same for the y's. 3t plus 1 equals 14s plus 6. And finally with the z's, oh excuse me, looking at it wrong. The y here was actually -2t. And then finally with the z's, we've got the 3t plus 1. Oh, I see what the problem is. I was looking and saw 2 j's. This should have been a j. K, not a j. That's what caused the problem. So one more time. We have set the x's equal right here. Now we've correctly set the y's equal, negative 2t and 14s plus 6. And finally with the z's, we've got 3t plus 1 equal to negative 21s plus 4. All right, so same deal. We would like to go ahead and see if there's an intersection point. So I'm going to rewrite this in its standard form. T plus 7s equals negative 3. Negative 2t minus 14s equals 6. And 3t plus 21s equals 3. And just going back to my calculator here, I need to change the coefficients in my system. 1, 7, negative 3, negative 2, negative 14, 6, and 3, 21, 3. And this time I get no solution. Which means the lines do not intersect at all. Therefore, they must be parallel. All right, one more. In part C, I'm once again going to have to go ahead and figure out what the V1 and the V2 are. So it looks like V1 is going to be 5, negative 2, 3. Always the coefficients of t. And for the V2, I'll get 10, 4, 6, the coefficients of s. And it looks like they're almost a multiple, but not quite, right? It looks like there was almost a multiple of 2, but this one's the spoiler. This one would have to be multiplied by negative 2. So V2 is not a multiple of V1. And that means that I'm going to have either intersecting or skew. To determine which that is, once again, we're going to look for an intersection point and see if we can find it. So once again, we set our x's equal. And looking up to the top of the page, that looks like 4 plus 5t equals 10s. For the y's, I would have negative 2t equals 6 plus 4s. And for the z's, 1 plus 3t equals 4 plus 6s. Get standard form. 5t minus 10s equals negative 4. Negative 2t minus 4s equals 6. And 3t minus 6s equals 3. So I'm going to enter everything into my matrix here. And we get no solution again. So I did not find an intersection point, and these lines must be skew. All right, that finally brings us to the end of section 11.5.